What again? um, I just finally no, I'm not gonna make a deal like that. Understood what this part does. So we know what a BC is. It's boundary conditions, and an IC is the initial conditions. Initial condition is for time, but why does this work? Is because when there's zero time, you're getting a function out of it. So in a certain, if you zero out the time, you get a function, and what zero? No, zero at the time. So if you get zero this, you get a function of this. But because there's no change in time, there must be one function of this to actually solve the equation. Well, a BC requires two of them. The part that confused me is why is it flipped? Why is it the second order in the x direction and then one first order in the other direction? Intuitively, my brain keeps on saying that it should be the opposite way around, but it's not correct then. It has to be this way around. So why? So you might be asking why does that? Why? The why part confuses me because if you have a second order, I was thinking there needs to be two solutions, but u is always a function of x and y. Over here, with an x comma t. Uh, and then over there, u is a function. So if we take a two derivative of that one function, we get one solution no matter what. And if I take a derivative of this t, well, I know that this is going to be zero. It's one derivative there, right? And if my stance is correct, this derivative will turn to 0 or 1 when I get x of 0 inside of u, because the only possible answer is a constant or 0. That's why t1 and t2 are constants, as we'll find out very soon. When I do this, T1 is a constant and T2 is a constant of T1, and T2 is a minus of these two to get this thing. And that makes sense with this derivative because if you think about it, what is the second derivative of the x direction? Well, you're going to either get a T1 as a constant, or, which I haven't done yet, both of them being 0, which would be which now I understand why the professor was so contemplating on teaching this concept. A rod that has different temperatures here, so temperature 1, a rod. If you look at this in reality, oh, I forgot I literally used Jamboard with snip to actually get that answer. So if you look into here with the segmented line over here, we're transposing it into a temperature line. So the temperature over here must be bigger than the other side over here to get this flux state, which also indicates the possibility that it's impossible for the flux to happen without temperature change. The difference in temperature allows for this to happen, and this is one of the points that I thought of, and I don't know if it's important at all. But it's basically saying that the temperature, because the temperature is fundamentally this, and then the flux is fundamentally this. If I remember correctly, temperature is fundamental that, right? Temperature. Let me make sure that temperature is that. Before I hastily say something that's so dumb that it blows the wires on some people. So this is Kelvin. So yes, U is specific temperature because Kelvin is temperature. And then, so yes, this U is temperature. That U with the density and the carbon specific heat turns it into energy, heat energy. So this part, if you do an integral of that, is turned into heat. or temperature. So temperature is what's needed for a flux to even occur, because we see from here, this side over here is literally just a flux, as we could tell. And more intuitively, the u in the derivative is, technically speaking, a temperature. Temperature. And a E that we talked about over here is energy, heat energy, heat. What was it again? Did I not write what that was? That's an oversight on my part. To not write that heat is thermal energy density is an oversight in my part. If I didn't write it, I swear I wrote. Here it is. Thermal energy density. Yes. Um. Yeah. So thermal energy density. That is the point that I am making here. If it's not understandable, we can go to a Jamboard and try. Oh, there is my graph I used to use it. Yeah, this is the graph I used to draw this out over here with the lines. But what I'm basically showing over here is that no matter what kind of wonky, so this one over here, I think the heat of there's a lot of heat over here. The temperature, if you measure it over here, was so high. Over here is lower, but it goes to this equilibrium because uh, one side over here is continuously being cooled down or heat up to that temperature, like a refrigerator. And over here, the same thing. Refrigerator and heater basically is both. There's a If we get a rod like this, which I am drawing horribly right now, there's a machine that's keeping it cool and hot at the same time to that temperature T1, T2, T1. So what's happening here is that we're trying to make a constant temperature. Well, in that case, there's another case that can happen where it's a straight line, the constant line, where everything becomes same thing. And that's when there's no interference from the outside world. So this basically becomes a linear line. We'll talk about that, and because I'm not done writing about that yet. It basically just says if you throw a hot rod, like it was on fire on one side and had cooling on one side, if you do it in space with an empty void, it will turn into a uniform temperature. The temperature can only be known by a starting value of zero and blah 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 blah. But for now, I finally understood this shit, so I'm stopping here for now. No, not literally. I'm gonna do that afterwards. But for now, we can safely assume what I'm talking about is truthful. Another thing to talk about, I guess, is this case over here. I'm not sure if this is correct, but what I'm telling over here is the force over here was purposefully made to be like this. It has to be, but as the chain is constant, I'm assuming that the pulley pulls on it more heavily, like continuously tightens it, allowing allowing. Oh, huh. I just realized this cannot be pulling over here, because if that's pulling that heavily, that means this line over here is not taut, which means that this shouldn't go this shouldn't make this this unsightly movement if these are plugs. So what I have to say is that they are basically stopped here, which means that they are plunked in. Um, it means that the line doesn't increase. So, um, in that sense, what would happen is that if this line is constant, what would happen is that because of the looseness of this, it would this is like a spring. Then this would be a spring. This would also be a spring. So what would happen? It would be contracted to side. It would be contracted because there's no point in occurring. It would be taunt. It's interesting. Actually, I think I have made this question wrong, made it made it complicated for no reason. But um, yeah, I'm gonna ask a professor on this one. I feel like I did something wrong here. This part is definitely correct because I said R was like the orange is a total force, so this part is correct. But this second part is a little bit off in my opinion. This is just joke. It's a joke. Yeah, I'm gonna have to actually figure that out if I ever get to it. Oh yeah, this one. Oh yeah, this one. I last time actually did it wrong. So basically, these are cylinder discs. This circle actually doesn't indicate anything except for that. Except for that, it is if you tilt your head and want to make it the same length everywhere, you would have to do that because otherwise you would never be able to get the same length everywhere. But in reality, it doesn't matter. I can give you the formula for that, and it's not part of the class actually. So um, it's a completely useless topic that I don't know why I mean why I would even care. But it was super interesting for me when it's part of solid mechanics. So it's basically later on, and it's completely useless and a trash question basically. It's not worth the question risking to even um, indicate what's happening here because it's not. Oh my god. Well, my notes are a mess, dude. So what's happening here is that the force applied is perpendicular to an angle because it's the definition of a shear stress. So what's happening is that it's being twisted and it's being broken. And if you look over here, it's tilting in that phase. And that phase makes it easier to look at the straight line. So if you tilt your head, it turns a straight line into a cube. This should over here should be a perfect cube, similar to over here when we did that. So actually, I did not. Oh, this is such an interesting question because in reality, it's not a perfect cube right now. Meaning, I did this wrong. I still got it wrong, probably. It doesn't look like it's hard to do with it's hard to show it with the limitations of how the uh it's hard to show it, but it's basically this is the square that is square over here. If I was to show this, I should probably have showed it over here somewhere. um you see how there's a cube there? I need another one. There's a cube over here, and that cube is transposed over here for some reason. It's not necessarily needed for this class. It's just showing that there's a shear force when you do this. Um, and that's the reason why it breaks eventually, unless it's malleable. It's not part of this class. It's actually pretty useless if you know this concept. So you don't need to know anything about it. You can just say you don't know about it until you get to advanced mechanics later on, where it's upper div course. So they purposely don't. I mean, they teach you it, but they barely teach you it. So I don't know what I'm talking about. So actually, I don't know how this happened. Let me fix this shit up. So what I'm gonna do is do this because I literally messed up here. I fully admit that I messed up a little bit over here. Um, I should have shown the other direction. It will be much easier also. So what I have to do is do this. The showing direction is wrong. So what I have to do is flip this around. And then that is way better. Yeah, I messed up a little bit on